Hi, my name is Francesco and I'm presenting here our results of the interferometric processing of Sentinel-1 data over a large area in South America. The context is in Helmholtz's project with the participation of DLR, the Remote Sensing Technology Institute, and GFZ, the German Research Center for Geosciences. The idea of the project is to produce a large library of INSA deformation products and to train with neural networks with physical models so that finally they can automatically detect and classify motion sources on real data. Here you can see the mean velocity map over the area that we've processed. And it's basically three long stripes for the descending geometry and three for the ascending geometry, plus a couple of slices on the northwestern part. It's a very arid and coherent area, so ideal for INSAR. And we have processed about 50 Sentinel-1 slices with PSDS algorithms. And we have applied ionospheric and tropospheric corrections. What you see here is the original INSA product without any GNSS calibration. This slide is to illustrate in a bit more detail the processing and post-processing steps. You see on the left that we have processed independently a number of slices for both the ascending and descending geometry, and you don't have any consistency in the azimuth direction. We have then an azimuth mosaicing step, which is really just a stitching of the products exploiting some overlap. And finally, we have a GPS calibration step. Here we have used the Nevada Geodetic Laboratory products, and this allows us to obtain absolute line of sight deformation rates. By combining ascending and descending acquisitions, we have attempted to do inversion for the east and the vertical components. What you see here is the mean velocity inverted for the east component. On the other side, the vertical component is a bit more problematic, and we think it suffers from a leakage from a large-scale north component. For this reason, I'm not presenting it here. Anyway, there's a number of prominent local vertical signals, as for example on volcanoes or on salt lakes. I'm going to give you now an overview of the different deformation phenomena that one can find in our dataset. An example here, it's a couple of examples of volcanoes with their typical rounded shapes. And sometimes also interesting over volcanoes to look at the time series, because we can see transient phenomena or nonlinearities in the deformation. We also have a couple of earthquakes in the dataset. Here you see one large and one small. We have mines. We have a signal which we interpret as a soil creep, possibly related to permafrost. It seems to have a dependency on also on thawing and freezing cycles, but also on precipitation. And also we have the typical uplift of salt pans. You can imagine that this variety of deformation signals poses some challenges for the machine learning detection and classification. In particular, the soil creep signal seems to interfere with the volcanic signatures and therefore requires some special treatment. And this concludes my presentation.